All right, welcome everyone to the webinar on guided labeling, human-in-the-loop label generation with active learning weak supervision. Today, myself, Paolo, Tamagnini, and Adrian, here it is, Adrian, will present active learning and weak supervision. So before we start, a bit of housekeeping. So, we have a Q&A section to post your questions, and you can use it to also upvote favorite question from other attendees. The session is also recorded and will be available on YouTube afterwards. So where is this Q&A section? If you go in the Zoom bar, you will find this button Q&A. And when you select it, you'll be able to make questions through such tool. Also, you can write the city where you're from if you want, and you see also other people. So please go ahead, do that if you want. But also make sure to make actual question as well. All right, so here we are starting again. I'm Paolo from the evangelism team at Knime, and Adrian Nembach, he's software engineer. I'm right, Adrian?
Yes, and hobby data scientist.
Of course. And today we're going to present to you those two topics and how to combine them together using Knime, of course. To start, I also would like to say that you can already find the slides at this link, tinyurl.com/guided-labeling. So you should also find the links I mentioned in the chat as I go through. So you can also pop up those material and go through them. All right, so let's start. So the total contents of today's webinar are active learning, that is human-in-the-loop analytics to generate labels and to train a machine learning model using a technique called exploration versus exploitation sampling. And that is an active learning sampling technique. And then we'll go through weak supervision. That will be Adrian's part, and what is weak supervision and how it works to overcome the problem of not having labels to train a model. And finally, we're going to combine those two together using what we call guided labeling, and we also demo a web application that does this in Knime. All right, so let's start now with the active learning part. So active learning. Before we can explain what active learning is, let's see actually where it stays in all these machine learning type of models we have there. So you might be familiar with this probably, but let's just have an overview again. Supervised learning, you have labels and you want to learn from those existing labels to predict the probability on some data where those labels are not provided. Right? Then there is unsupervised learning, that is clustering, dimensional reduction. You don't need those labels, but the output won't be as precise as with supervised learning. And then we have also reinforcement learning. That is different. You can use reinforcement learning also for classification, because that's the machine learning task that we want to do, to classify. And reinforcement learning has the possibility to run an experiment, measure the success or failure, and with a feedback loop, improve the model each time to perform this operation correctly. Now, active learning stands in these categories right here, supervised learning. So what about supervised learning? Well, supervised learning needs lots and lots of training data. And what about this training data? We need to require a proper sample, so enough data that describes correctly the reality that the data is about, the real world scenario. And also it doesn't need to be, that's the idea to not be biased then. And also you need to have labels on this data, like we were saying, to train a supervised learning. And you can see this star here and lots. This is for deep learning, right? The deep learning is actually a kind of supervised learning you can do where you have a neural network with many, many layers. But in this case, to make it work, you really need a lot of data and a lot of labels. And where do those labels come from? Well, there are different scenarios here, and let's now go through them to have a full overview. So you can have luck to find them on the internet. There are many, many portals where you can find public data set, and you can join your data with these open data sets. And the idea is that you might get lucky, but it doesn't always work. An example, if we talk about documents, the European Union releases all those documents in several languages, and they're open for everyone to do really cool things with them. But again, this is just if you get lucky. Another possibility is to pay people to label. And in case of students, you can also maybe give them a free t-shirt. And there are platforms to get the labels from all those different sources. One of those is Amazon Mechanical Turk. This goes towards the idea of crowdsourcing your labels. And this can be possible when it's relatively easy to find someone that is actually able to label your data. Okay, so what else is out there? Well, as a funny example, you can cheat people into labeling. So you might be familiar with those interfaces you find online as you surf the internet. Sure, they want to find out whether you're a human or not, but in the end, you're actually labeling a data set for someone. So there are also this crazy way to do it. But then let's go actually to the label source that we want to focus on, the experts. Experts is when you have only a kind of user that has really particular domain knowledge, and it's somewhat hard to find, and that also make him expensive. And this can be, for example, doctors, if you think of an healthcare data set, or someone expert in finance and so on. Domain expertise can be a lot expensive, and often this is what you need to label your data. So active learning is focusing on these categories, using experts to label your data efficiently. So let's rephrase a bit, what is our data science problem here? We want to train a supervised machine learning model, but we need to use less label than we would usually need. And that's because we want to save money and time because we are using an expensive expert and also easily bored, right? And just to make it a bit more complicated, we say that we start with no labels at all. So how do we do this? And the answer is with active learning. So we have a starting situation with lots of data points, and that is the input, the features of our data set, and no labels. No, that's the point, right? We start with no labels at all. And we initialize the active learning loop by picking some data points that are still unlabeled and just showing them to what it's called in active learning literature, the oracle. So the oracle, the expert, looks at those data points and he can label them, just a few of them. And then we can actually start the active learning loop. And when we started, we can train a model on this really tiny set of labels. Of course, the model will be really biased and with not such a good performance, but it's something to start with. And then we can apply a technique to select a few critical data points. And then we show them again to the oracle, to the expert, and we repeat this process. That's the idea of human in the loop. The idea where you have an oracle that labels that is a human, and the human alternates his task with the machine, with in this case, the machine learning model that is retrained each time. And this cycle is also to improve the system, because by alternating human and machine, you end up with training a supervised model with less label than you need. As you can see, the key parts here is the selecting few critical data points that really the human can look at, label, and improve the model better than by just selecting random data points. And that's the key part of active learning, the active learning sampling. So the point is, how do I select critical data points to be labeled? And actually, how do I do this intelligently? And that is because we don't want to do this at random. Otherwise, why go through the effort of having all this human-in-the-loop complex system? We would just label as many as we can with our expensive expert and then train a model. We don't want that. We want to do this intelligently. So there are two techniques to do this, to select the data points to be labeled. We use label density and model uncertainty. And we are going to focus first on label density. So what is label density? The idea is that you want to label first in areas of the feature space. So in group of rows that are really close to one another, so that you don't waste time labeling rows that are really unique. And that is basically, you can say that this is meaning to label in dense but unexplored area of the feature space, because you don't want to always label in the same places. So we can initialize this with a prior distribution. And this is especially useful in the beginning when the model has really few labels, and so it's really not performance enough to tell us something useful that we will see later. There are different functions to do this. What we use in our application, but there are also more available in Knime, it's called subscriptive clustering. So the idea here is that you see this formula, it might be maybe boring or scary to you, but it's rather simple. For each data point, we compute a neighborhood by measuring a radius around it in the feature space. Then we take all the data points within this radius and we compute the distance. And by using this distance, in this case an Euclidean distance, you compute a score for each data point to how dense is its neighborhood around. All right, so how do we actually see this in the feature space? I made an example for you, so it's rather easy to understand. So let's take a data set only made of two columns, two features, height and weight. And each data points you see here is a person, right? And that's easy to visualize. Actually, I visualized this using a 2D density plot, using a plotly node in Knime. And when it's only two columns, it's easy to tell that the really dark blue area of this visualization is where the density is super high. But this algorithm, that also works with more than two columns, is actually telling us this the same without visualizing anything or asking a human where the feature space is dense. And so it will tell us label right here. And this is then the point of finding data points in dense areas. But if we keep using this formula like this, we're going to label always in the same points. And so we need to update this rank by reducing it when we have new labels. So at each iteration, we are going to reduce this density score. And we are going to reduce only where we have a neighborhood with already existing labels. So what does this mean? It means that even if in the first iteration I label up there in one of the dense area of the feature space, in the next iteration, I'm going to label maybe down there, because also there you have high density. And that will bring with way more features and a way more complex feature space, a way to explore it iteration by iteration, and always show new cases to the human in the loop. Okay, so let's go now to the second topic, model uncertainty. How do we actually use model uncertainty to do active learning sampling? So we want to label first where the model is really uncertain. So this means that we are going to initialize with random predictions, because in the beginning, the model is not certain about anything because it doesn't exist yet. And then this gets refined as the model achieves a good performance. And when the model has achieved a good performance, you have a measure to where it's sure of its prediction or not sure at all of its prediction. And the intuition behind this is that the human can offer the more help to the model when the model is not sure of what label should be predicted. So as a function to do this, we can use the prediction entropy. And this is basically by taking the vector of probabilities coming out of a model and compute the entropy by applying this formula. Let me show you a quick example to how this formula works. So let's say that you have two rows. One, it shows a model, the model is really sure of label 1. So 90% for label 1, 5% for the other two labels. Then you have row 1, the second row, you have instead a probability of 33% each. So you will see the entropy score is higher where the probability are more or less all equal to one another. And instead entropy score is lower when instead the model is sure of its prediction. But then which are we picking first to show to the user to ask the label? Well, the second row, because the entropy score is higher. So that's how entropy score works. All right, so let's now take again the example of overweight of height and weight of people, and let's use the body mass index, which you can find on Wikipedia, that is dividing sort of in two classes, underweight and overweight. This is only a simple example. Let's not get too much in the domain here of the data of what means overweight, underweight. Let's just think that with the body mass index, we can split somehow people between those two categories. And we want to learn with a model, starting with no labels, such decision boundary. So first of all, what does it mean, model uncertainty in the feature space? We know what density means, but we don't know what model's uncertainty means. So let's take, for example, a model at iteration k. You can see that this decision boundary is not so close to the one we had before, but it's still some way getting there. We are at iteration k, and we want to use model uncertainty to decide what should we label next. So the idea is that with model uncertainty, there is low model uncertainty if you go away from the decision boundary, because the reason the two classes are really well distinct when you go away from the decision boundary. So you can see that, for example, in this area of the feature space, you have a probability of overweight that is pretty high, 100%. While instead, if you pick data points around the decision boundary, you will see instead that the model is not so sure of this distinction. So the intuition is that you will have instead an high model uncertainty. So the idea is then that we want to use then data points around the decision boundary to exploit them and quickly find misclassification by the model and move to the decision boundary that is closer to the real one. So by taking those decision boundary using model uncertainty, they are close, those data points close to the decision boundary using model uncertainty, we're going to go to this other decision boundary that is closer to the actual one. So that's how it works, model uncertainty in the feature space, and it's all about exploiting those key data points that are near the boundary of the two classes. Okay, so now we understood those two techniques. One is called label density, and we're exploring the feature space, and one is called model uncertainty. And here we are instead exploiting data points to find the best decision boundary. So how do we combine them together? So there are a couple of papers that show how to do this. And how do you combine two formulas? One is subscriptive clustering, one is entropy score, but we could have picked different measures. How do we combine then the exploration score with the exploitation score, or with another formula, what we call the estimation potential? So we have here the two formula summed together, and there is this epsilon parameter here. The epsilon parameter is it goes between 0 and 1, and it gives how much it contributes each score. So if epsilon is 0, then you have a density score that is only using the potential score. If epsilon is 1, you have instead only the exploitation score. So why is this epsilon important? Because the idea is that in an active learning loop, you want to use potential, the two techniques together, but you also want to go from exploration to exploitation. Why? Well, in the first iteration, the model is train on really few labels. So it's not going to be as good. So you want to explore first. Also because most of the feature space has never been labeled before. So you want to go on and explore using the density score. But then, after a few iterations, you will see how the model performance increases and you don't see the decision boundary moving so much. So you want to start exploiting those key data points that will bring us to the final decision boundary and then do exploitation. And you can do this by changing, given the number of iterations or some other heuristic that some other thing that you can do is stopping. And the stopping criterion, that's hopefully the idea, right? That you don't need to label forever because at some point the model will be good enough. So you can see the potential. So when the potential score is low everywhere, then it's a good point to stop labeling. But of course, what is this threshold? It will really depend on the use case. So it can be tricky to define the threshold. Another thing that you could do is simply stop whenever the user is tired of labeling, or ask the user to simply check for the model performance if it is high enough or not. Okay, so a simple demonstration here to see how active learning is useful. Again, let me take this really simple data set with this really simple linear decision boundary. The idea is that you have underweight prediction and overweight prediction, and we want to train a model to learn this body mass index decision boundary. I think it's greater than 25 or less than 25. It's not perfectly linear, but it's almost linear. So how do we learn this decision boundary? Well, it's a really easy problem. You could do it really quickly, but we want to put a constraint here to show why active learning is useful. We want to learn it only on 10 data points. And so to do this, we need active learning, because to learn this line only from 10 data points, we need to select them well. And of course, automatically, not by a human that selects them using, I don't know, for example, this image. So the idea is then to use active learning, and active learning can get you with only 10 data points to a decision boundary that is actually quite close to the real one. How do we compare this? Well, we could compare with a random strategy, for example. So if you would just pick 10 random data points and then train the model, this could happen, for example, right? You have a model that is trained in a way that is almost perpendicular to the real decision boundary. So this is just a quick example to show you how active learning is useful, and how it's using density to label in dense places, but also along the decision boundaries, how it gets recomputed. And you can actually play with this example yourself using Knime. So I used those nodes, the active learning extension with Knime. As you can see, we have the density initializer of 2 types. And this is actually the one that I showed the formula for. And then there is the density score and updater to actually make sure that you have a score for each row, and also that you are going to update given the labels you already have provided. Then you have an entropy scorer, and entropy scorer and the density score can be combined in the exploration versus exploitation score using this other node. And then you have the top case selector to decide what should be labeled. And also a view to label if you have a human labeling. The active learning loop is how you iterate everything. So let me show you the example actually. This is the workflow for the body mass index. You have here data with weight and height of people. You have on the top branch, you're going to have those 10 random data points, then labeled not by a human, but using the body mass index, and we just use a column expression here. And then here you train the SVM model on those 10 random data points, and then you score all the unlabeled data points. You do the same here, just the data points are being selected, are selected using active learning. So here we train the model in here, then we label the selected one. In here we have all the score, the exploration score, and then we update the density score. And then here we start with train data points for initialization, and we iterate this 7 times. We have 10 labels here. We train the SVM, and then we score. So what is this final component here? Well, this is actually to interactively compare the two strategies. You can see already from the arrow C up here that the blue one, the active learning model, is much better than the green one, the model trained with 10 random data points. And then you can also use this binary classification inspector node, interact with the plot, and see the misclassification in the 2D density plot below. All right, so you can find this workflow on the hub, and you should be able to find in the chat this link, or just type on the hub body mass index, and you should be able to find it. All right, so this is for active learning. Let's now see the next topic with Adrian, with weak supervision. So I'll stop sharing so that Adrian can take over.
Yes, let me take over.
All right.
Thank
you, Adrian. Let me stop my...
Okay, thank you, Paolo, for this nice introduction to active learning. In the next part of this presentation, I'll talk about how we can use weak supervision to blend knowledge from different sources. So the inspiration for the title of this part comes from our popular blog post series, Will They Blend?, where we have lots and lots of blog posts on how to combine different different sources of data. So you can use databases or some online service where you can get your data from, and you can combine it. But it's really not about combining knowledge in the form of labels. So you could imagine that you can get labels from a database and labels from some online service, but how do you combine them if you have conflicts, for example? And this is where weak supervision really can help us. Click. Now, before we go into the details on weak supervision, I would like to highlight some limitations of active learning. So as Paolo showed, active learning is this iterative process where you label data points together with feedback from the model, basically. So the model picks which data points it wants to see in a certain way. And this approach really focuses on having a good quality of labels, but not necessarily a large quantities. Paolo already mentioned that in the beginning. There are some approaches like deep learning that require lots and lots of data. And here I listed some examples for how this works. Okay. For example, to train those now popular convolutional neural networks, you need the ImageNet dataset, for example, and it contains 14 million images. If you have to label all of them by hand, then this will take a while. Well, it took a while. They are already labeled, so this might be an example of where you got lucky with your labels. But in many cases, you really have your own data, right? That you get from your customers or some other source, and you don't have labels, and then it gets tricky if you have to label millions of data points. And even if active learning is one way to get very high quality labels, it can take a long time to get a lot of those. And you need a lot of those to train a deep learning network because it has so many parameters. Now, weak supervision was introduced as a kind of remedy for this problem. And it is defined as a branch of machine learning where noisy, limited or imprecise sources are used to provide supervision for labeling large amounts of training data in an unsupervised, in a supervised learning setting. It was developed at Stanford University by Alex Ratner and his colleagues, and they also offer a Python package that you should definitely check out if you are using Python. It's located on the Snorkel website, and if any of you finds out where this name or the icon comes from or the logo comes from, please drop me a mail or maybe a message on LinkedIn, because I tried to find that out, but without success. I kind of get the octopus because it pulls in knowledge and information from multiple sources, but I don't get the snorkel part. So please let me know if you happen to know. Okay, now the definition I showed before is nice if you already know how it works, but it doesn't really bring across the intuition. And I think here this graphic, also provided by Alexander Adner and his colleagues in a blog post for Stanford AI blog. They show how the idea behind weak supervision is structured. So you have your domain expert on the left-hand side, and then this domain expert provides you with labeling functions, and those labeling functions provide you with so-called weak labels that are aggregated using a generative model, which in turn outputs probabilistic labels that you can then learn your deep learning model, for example, from. If you didn't really get all of that, then don't worry. It took me quite a while to just figure out how this works by only looking at this graphic. So I will quickly show you a small example. Now in this example, I'm really looking forward to going to a restaurant with friends again. And we assume there is this new restaurant in town called Rüdiger's Pizzeria. And I want to know if I should go or if I shouldn't go there. So basically if it's a good or a bad restaurant. One way I could figure that out is going on Google or Yelp and just check out the reviews. But if you're like me, then you maybe made some bad experiences with the reviews on Google, especially if there are only few, then it seems sometimes they can be quite biased. So I instead ask a couple of friends for their opinion. And one of those friends is Paolo, so I ask him, is this Rüdiger's Pizzeria any good? And Paolo really knows his pizza, and he's like, yeah, no, it's not. This is not really a nice Italian place. But I also ask some other friends, and they tell me, no, actually, it's quite a great place. You should go. And one person hasn't even been there, so they can't say if it's good or bad. If I trust everybody equally, then I will have to go, or I have to decide that it's actually kind of a good restaurant because the majority vote is that it is good. However, this already contains this assumption that I trust everybody equally, but maybe Paolo really knows his food, or his restaurants, so maybe I should trust him more. But how do I know who to trust more? Well, from experience, probably. So let's assume we don't only have opinions on Rüdiger's Pizzeria, but also on Franzel's Sushi and Hildegard's Bry, and also a couple or more restaurants. And all of my friends give their opinion on those. Then I can basically look on how those opinions agree or disagree in order to figure out if one person is more likely to always say something is great, for example, or another person might say, yeah, no, everything is bad. And then if they actually say, no, this is a good restaurant, then maybe you should pay attention. Sorry. Yeah. The question now is, how can we actually use this? Because as data scientists, we would like to train a model. So I don't want to carry around my friends to ask them for their opinion on restaurants all the time. So instead, I could just train a model and have it on my smartphone, for example, and then I can ask the model. So the question is, how do we get from these kind of multiple sources of labels to a trained model? And the usual paradigm is that your models your model is trained on like one source of labels. So you have, for example, only one of those columns or one of those people that give you opinion and you learn from that. But then how would you combine those models in the end? So a different approach is to just combine the labels. And this is done using, well, of course, weak supervision. And here we see this kind of generative model which I will explain in a second. But before that, I would like to take a minute and talk about the different label sources, or weak label sources, as we will call them here. And really what my friends are doing is they act as functions from restaurants to labels. So they can say the restaurant is good, the restaurant is bad, or they can say I haven't been, so I don't really have an opinion, right? And well, what I now need in order to combine those opinions is some way of figuring out how accurate my friends are. If all of them are equally accurate, then I can just basically take the mean or the majority vote in a certain way. But if they vary, then I might want to adjust that a bit. So for example, if I trust Paolo more with his judgment than some of my other friends, then I should weight him more. And the idea is to figure that out, right? But instead of my friends, I could also just have some simple rules. Not to say that I want to replace all my friends, but if I have to carry my friends with me to kind of figure out all the restaurants, or actually if I have a huge data set of restaurants and I want all of them labeled so I can train, then having all my friends label them won't give us an improvement over the idea of active learning, where I said in the beginning that, well, a limitation is that it takes a lot of time. But if I have rules that I can apply, then I can just apply those rules to millions of data points, and with modern computers that will just take like a split second to compute. And one such rule could be, if we have a restaurant in a certain district of town that is very competitive, then the restaurant must be very good if it survives there for a long time. I mean, obviously this is not always true, but we just need something that is basically better than random guessing. And you could think of a lot of different kind of label sources or labeling functions like this. So we had the simple rules, but we could also use existing knowledge bases. So I could actually take reviews from Google and integrate, or ratings from Google or Yelp, and integrate them as one labeling source. And I can have this kind of rule where I say, well, if it's only 5 people that rated there, then I don't trust that rating, and I'll only take ratings for places that have, I don't know, over 100 ratings. And you can also have existing models. So suppose I trained a simple decision tree a couple of years back on a very much smaller data set with a subset of the features or something like that, then I could still use that model now and integrate that knowledge into a new model. So I can just combine all the information. And if you think about it, you can take really anything that can provide you with labels and is better than random guessing. Because if it's just like, if the labeling function or the label source is just guessing, then there is no real use to it, and you might just as well save the computation. All right, now for the generative model. So this is kind of the filet piece of weak supervision. And it's based on Bayesian networks. I hope this doesn't scare any of you. Actually, it turns out this is the simplest Bayesian network that you can come up with, also known as naive Bayes. You might have heard that one, although the true naive Bayes is the algorithm how it's learned is very different. So the cool thing here is that we train this kind of naive Bayes model where we have variables for our label sources. So I have my 4 friends here on the left, and then I have the true label y that we kind of want to figure out by just learning the accuracies of my friends, and then using those accuracies to weight their labels into one combined probabilistic label. As I already said, this is a naive Bayes model, which essentially means that it assumes that all those labeling sources I have are independent. That's quite a strong assumption, to be honest, in theory, but it turns out in practice, this assumption holds in many use cases. And it's actually the case that the Snorkel Python package also makes this assumption, even though they have in the papers sections on how you can integrate this correlation information. So it's possible to integrate it, but it's much more expensive in terms of runtime, for example. And it doesn't provide enough gain, or at least the downside, the upside apparently isn't as large as you might imagine. So it tends to work quite well in practice. As for the exact algorithm that is used here, this is a matrix completion style algorithm, which I won't go into the details of because it's quite mathy, and yeah, you have to like math a lot if you want to have the details for that one. I can recommend the paper though. It's here at the bottom, listed here at the bottom. It's called Training Complex Models with Multitask Weak Supervision, and it was published only last year. Check it out if you are interested in how this approach works in detail. Great. So now the question is, how do we get from this generative model or weak label model to given our weak label model sources to our probabilistic labels? Well, it's actually quite simple. We have the labels from our sources, and then we use the model to kind of weigh them and combine them into this probabilistic label. And the probabilistic label means it's not a strict label like it's a good restaurant or it's a bad restaurant, but instead it's a probability distribution over the classes that you have. So you basically say, well, this restaurant is 60% good, but it's 40% not so good or bad. And then you can actually use this to train. Obviously, the question is, what kind of classifier can we actually train with that? And the answer to this question is, well, actually quite a few. There's logistic regression and also deep learning. Those two are very closely related, so it's obvious that if one works, the other will as well. But there's also gradient boosted trees, random forests, and decision trees. So these three are actually very useful for tabular data, where deep learning just is not as powerful compared to other methods when you switch domains. For example, for images, you basically have to go with deep learning now. But if you have tabular data, gradient boosted trees and random forests are very good alternatives that are much quicker to execute and learn. For random forests and decision trees, there is actually a slight limitation because their heuristics that they use internally don't learn probability distributions directly, but you can adjust them so that they do. So that would be possible in practice. All right. Now for Knime related nodes that use this approach, we added the Knime Weak Supervision extension with the last release, as Paolo already mentioned, and it basically contains only two nodes: the weak label model learner that does the learning of the generative model, and the weak label model predictor that applies the model to your data to get those probabilistic labels. And then we also adjusted a couple of other nodes so that they can actually deal with this kind of probabilistic label, namely the gradient boosted trees learner, the logistic regression learner, and the Keras network learner. All right. Now, I would like to show you an example for how you can use weak supervision for the use case of document classification. And for this, Paolo created a very nice workflow that is also on the hub. So you can just type in weak supervision and document on the Knime hub, and you will get to this nice workflow. Before I show you the workflow live, I would like to give you an idea of how we define the labeling functions here. So the idea here is that we create relatively simple rules in an interactive fashion. You will see that in a second. And those rules are basically, if some word is contained, so for example, if awesome movie is contained in a review, then the review is positive. So we are doing sentiment analysis. And then if we get a review coming in that contains this phrase, awesome movie, then we classify it as positive. Mind you though, if we have a very similar review that doesn't contain this phrase, then the labeling function doesn't apply, so it can't label it. So it will actually produce a missing value for it, which is equivalent to saying, I abstain, I don't know the label. So what you get if you apply a couple of those rules is this kind of table where you have lots and lots of missing values, and then a couple of labels for your different, provided by your different labeling functions. So in this case, it would be 8 labeling functions. All right, now let's check out the example on the Knime web portal. So I don't know how familiar you are with Knime and the products that we offer. The Knime server is our commercial offering that comes with, in some configurations or in the bigger configurations, comes with the Knime web portal, which allows you to deploy your workflows you created with the analytics platform into a format that is much more wizard-like, and you can then click through it. So if you have users that don't want to install the Knime analytics platform, you can upload workflows, or you can create workflows that perform certain tasks, upload them to the web portal, and then have them run through them there. So I will just start this workflow here. Don't worry, I also have it down here, so you can actually download this and run it locally as well. But I will show it here in the web portal. In this workflow, you only have basically 3 steps. The first step is to upload your data. In this case, if you just want to check out the example, just use the defaults. It comes with some IMDb data set, basically from the get-go. And you define which kind of classes you have in this data set, and then you can start it. Now, what is happening now in the background is that Knime does some pre-processing. So if we go to Knime, I can actually show you a different feature. So I can show you the remote job view. So if you have your Knime analytics platform connected with the Knime server, you can look at the jobs while they are running. And here we can see that we have this upload step we had in the beginning. And then there is some text pre-processing happening because, well, we have some text that we want to classify. And then we are in this next step, which is specifying the rules. So luckily, Paolo already provided us with a couple of simple rules that we can use. So we have some words like worst that indicate a negative review, or amazing, which would indicate a positive review. I will just add like 2 more, for example, great. We had that on the slides, right? And also hideous, which is obviously not so positive. All right, then we can continue. I will quickly switch back here so you can see what is happening behind the scenes. So once we have the rules, we split the data into a training and a test set so we can evaluate how well the weak supervision worked. Then we train the weak label model. So this is this generative model that figures out the accuracies of the labeling functions. We then apply it to get probabilistic labels. Then we train the gradient boosted trees learner, predict the test data with it, and then we actually compare it with the bottom branch. And the idea of the bottom branch is, well, if I have those rules, I basically already have a model, right? This is kind of an ensemble model because I can apply it to unseen data, then use the weak label model that I trained on my training set to combine those, and I also get predictions. And obviously the question is there any use in training this discriminative classifier after already training this weak label model? And if we go to the web portal, then we see that we have this binary classification inspector that Paolo already briefly showed before. And we have a discriminative model and a generative model. And just by looking at those scores up here, we see that the discriminative model is actually slightly better. So these are the gradient boosted trees. And this is the model that just combines the labels using the generative model. So if I actually click here, I get some more information. So I can see the confusion matrix for my model, for the discriminative model, and the distribution of class probabilities. And when you play with this, you can also click here, for example, on this quadrant up here, and you will get the reviews where you have wrong predictions, for example. All right, good. I could actually play with this the whole day, but I won't, I promise. I'll just quickly show you how to do it when you are in a local installation of Knime. There you also have those 3 steps. And in order to go through them, you just open the interactive view. There you can specify all of your information. You can close it and apply the settings. Then go to the rules, add your rules, close and apply the settings, and then you can open the compare, the final compare step, and see how your rules actually worked. Good. With that, I'll quickly switch back to my presentation and go through 2 more short topics. The first is, when does weak supervision work or make sense? And there is actually a paper on this, again by the Stanford group, where they try to answer exactly this question. And what they found out is that it tends to work very well if you have between 10 sufficiently nice labeling sources and 100. If you have fewer than 10, then it's really hard to figure out the label source accuracies just from the overlaps on your data set. And if you have more than 100, then the rule of the wisdom of the crowd really kicks in, and you can't basically outperform using the weak supervision approach. One side note here, this is not really surprising if you have been dealing with random forests, because 100 forests is also around where random forests start to converge to the optimal probability. So the idea in random forests is you train lots of decision trees and you just average over them. And the reason why this works is the rule of the wisdom of the crowd. And the same thing applies here for your labeling function if you have many, but you still have to come up with all of those, right? And hopefully you don't need to come up with those, but you cannot come up with like 20 or 30 and you are done. Now, I said that those have to be sufficiently nice. As I said before, the assumption right now is that those labeling sources are uncorrelated, which in practice seems to hold very well. And it's actually also possible to integrate this kind of correlations. So there are papers on this. It's just not in the production version of the code yet. Perhaps because there are still some limitations in that area. Your sources need to overlap, because if they are all exclusive, then you can't really see which sources are more accurate than others. And they shouldn't be too sparse. This might actually be one of the problems why we didn't see a larger gain of the discriminative model in my example that I showed, because many of those rules are very sparse, so they only apply to very few data points. And if a model only applies to 2 data points, it might just be right out of luck. So you can't really tell if it's really accurate or just lucky. And lucky just means it would be random guessing, right? And as I said before, if you have a source that is just right by chance, then you might ignore it and save the computation time. And you should also not have adversarial sources. So an adversarial source is a source that is wrong on purpose. So if you have 100 sources and one of them is adversarial, then weak supervision will be able to figure that out and just assign it 0 accuracy. But the more balanced this kind of distribution between adversarial and non-adversarial is, the harder this gets, and you can't really tell, or weak supervision can't really tell the good from the bad in that case. All right, now I talked a lot about weak supervision, and I would like to find my way back to active learning as well, with the question of which one is better, active learning versus weak supervision, and do we really have to pick, right? Is this like an or can we actually just combine the two? And obviously we can, right? Because active learning is this iterative approach, and in weak supervision we just combine multiple sources. So those two are not exclusive, we can combine them. For example, we could have our domain expert who provides us with simple heuristics that they will also use themselves when they label data. So in many cases, you can come up with very simple rules. For example, well, if the review contains the word great, then it's positive, right? And then we can use those rules to label lots and lots of data points and actually leave only those data points for labeling, for hand labeling, where the model struggles. So actually the user only has to label those data points that can't be labeled using the simple heuristics, because those are really difficult data points. And we can also improve our heuristics over time. So before I quickly showed you how you can search through the data points that were classified incorrectly. And by doing that, you might be able to see like, oh, this word seems to come up in many of those, and it would actually be a good indicator. So you can just make a rule in the next iteration that will pick those rules, those data points right, and those improve the probability that your model actually also figures them out. Alternatively, you can also have this scenario where you have multiple users working independently of each other in the beginning, like here, and then you can combine whatever they come up with into one big data set using weak supervision, and then train your end model on that one data set. So on the left here, what was on the bottom on the previous slide, we like to call something like crowdsourcing guided labeling. And on the right, we see this kind of human in the loop guided labeling that you might have seen before if you listened to one of Paolo's conference talks. And in general, guided labeling for us is an umbrella term for things like active learning and weak supervision that allow you to get your unlabeled data into a labeled state where you can use it for training your models. And now actually Paolo will show you this an example of how you could do this human in the loop guided labeling here on the right, also on this example of document classification. Thank you very much for listening, and I'm looking forward to your questions in the Q&A
stay
later.
Until the end, guys. We have the questions. All right, can you stop sharing? Thank you. All right, so sharing the screen again, and here we are. No, that's a spoiler, and here we are. So, guided labeling for document classification. So this is another guide analytics application that is running on the web portal, and and it's still for document classification. So we are combining the two ideas, right? One is the labeling functions for weak supervision, and the other one is active learning. You have unlabeled documents coming in the application, you have the human in the loop, and the model trained use weak supervision, and active learning providing the right labels, the right documents, the critical data points to be labeled next. And then you can have on the outside the final data set and training model. Now, we could use still the movie reviews example, but I find that this maybe, I don't know, in Europe is getting kind of late. I would like to have a more exciting example. So I already presented this ODSC West in San Francisco, and it was Halloween. And so back then it made perfect sense to make this personal use case or movie classification. Why? Well, not just because it was Halloween, but also because it's a perfect example. I'm the only person having domain expert to classify or movie based on whether they are actually scary to me or they are instead funny to me. So how does this work? We are going to have, for example, a movie that has a low-budget movie about a vampire family. For me, vampires are actually, to my own domain expertise, for which I only can give label, for me are funny. So I want this classification to scare them, to classify them as funny. And then we have instead a movie plot that is about zombie and apocalypse. I find this really scary. So I want my model trained on this data and on my own label to instead provide the classification scary. So as you can see, I just made it up, but that's what the application can let me do. So let's see actually how it works. So like Adrian, I'm opening my web browser. I access here the workflow with the guided labeling for document classification. And here we start the application. So at any minute, it should start now. And the first page is really similar to what Adrian showed. Just that this time, I want to change the data here. I want to provide documents from our movies, not movie reviews. So here we are. And then after providing the our movies plots, I want to change the labels. So the class name will be the first one we said funny, and the class abbreviation will be instead like this. We want to have a small label, and I think this is a really good abbreviation for funny. Then we can have the second one, scary, and the abbreviation will be the following. Okay, so now we have unlabeled documents, we have possible labels. Let's go ahead and provide the rules. Actually, let me put this to full screen. Nice. So now we are creating the text processing step. Bug of words, stop words removal, stemming, all of that part of the text processing extension of Knime. Have a look, we're not gonna focus on that now. We have documents, we need provide labeling functions. But I don't want to use this from the sentiment analysis. Let's provide different labeling functions. So how will I do that? Well, I need to say, for example, that's my own labeling function. Vampire are really funny to me, and I will use the abbreviation. And instead, zombies are scary. And let's say apocalypse also associated with zombie. I find this also scary, and Dracula instead is funny to me, at least. That's my own labeling function for my own person model. Okay, so we have some labeling function now. Let's go ahead and see what happens. So now we are accessing the human in the loop. It's not like just like before. Model, train, labeling functions, we have a model. Now we need to provide more labels. This is just the start. We start the human in the loop, and at each iteration, we're going to provide more labels, and we can have a number of ways to do this. We have the average density, we have the average entropy, we have the average potential, and we have here this labeling view that will give us the possibility to labels either as funny or as scary. We can read the document, we can go through the labeling functions here, and at the bottom, we can also see the labeling function correlation. Zombie is really correlated with apocalypse. Okay, so let's now provide some labels as we would be doing in active learning beside weak supervision. So here is about infested woods, killer. It's about a party. I think this is funny. Then we have here 4 astronauts are about paranoia. I think this is scary. As I end my thing. Oh, this is another one. I don't know. I'm going to skip this. And again here, a jungle party in Peru. Come on, this must be funny. Inaugural party of one of the largest malls in Asia. Oh man, why do I need to always label as funny all those documents? If I want to go back to those documents, actually, I can select here to show more of them and actually to see them here listed. Those are the labels already provided, and I also skipped one of the labels. Okay, so, but you know what? I don't want to always label the ones that come as party as funny. I'm just gonna write down here, if party is in the movie plot, then I'm going to automatically use this labeling function that labels them as funny. And then I can click next. So what's going to happen now is that I'm not just going to be over. This is just the first iteration of the human in the loop. I'm going now to the second iteration of the human in the loop. How do I know that now? Because it says up here, label iteration number 2. Now I have also this tag cloud. I can see that party is something connected to funny movie. And I can also see that instead fear and death are connected to scary movies. So we can use this tag cloud to select, for example, more data, and we can do this in a number of ways. But it's also important to see here how this updated. Now we have a new labeling function called party. So as you can see, we can also have all of this interactive, find the correlation between one that was selected, and for example, find the aggregated functions to this. This is all built with Knime nodes and can be customized. Let's say that we stop labeling now. I do go on stop labeling up here, even though the average potential is 72%, is still quite high. Let's, just for this demo, let's decide to wrap it up after 2 iterations and export the model and the labels and the labeling functions. So I click next, and now I'm exiting the human in the loop, and I go to the final page where I can download the labels, I can download the model, and I can also compare the labeling of the human and the labeling of the model using those tag clouds. As you can see, the human really likes to find, it's really biased, this tag cloud, on the really few labels we provided manually. While the model that also uses labeling function is using all kind of words to label things. For example, you also use party, that's good. But this is only an example. Let's not take too much time on this. And of course, it's all interactive, and you can select and browse documents this way. Okay, so let's now go back to the slides and start presenting again. So this was used for binary classification, and binary classification can be used for documents, at least in a number of ways. We could have used this for sentiment analysis as well, like its default settings. So the tag cloud would have shown sentiment, and this can be used with any document you have from, I don't know, for example, social media and tweets of Twitter and so on. Another thing you can do is to use this for multi-classification. So for example, you have articles, could be also like legal documents, whatever, and you want to classify them in different topics, but you do not have any labels to train your supervised model, then you can use this application. For example, you can see here in the screenshot that Trump is used a lot to detect documents that are talking about politics. And this is for topic detection. All right, so as Adrian already mentioned, this is about you creating a workflow, and this is done with a free and open source Knime analytics platform. And this workflow, it is in the end a guide analytics application. Yes, you can export the workflow, send it to someone, and then he's executing it on his own Knime analytics platform for free. But of course, it's much more handy to take the Knime server, the Knime workflow, and deploy it on a Knime server. Why? Well, because in the end, this is the perfect way to deploy it. People can just use the Knime web portal as a final place to access the workflow, and using this wizard application to label and log in and so on and so forth. All right, so this is the paradigm for all the analytics application with Knime, and we have many automated machine learning, automated visualizations. We have a number of those, and their story is always the same. Create the analytics workflow with Knime, deploy, access with the Knime web portal. So this is the workflow I used for this application. I created this totally on my own, and actually maybe some help here and there from also other Knimers, but let's now go through this workflow. For example, we train in this particular part the model. So if we open this meta node, we can find more nodes. And inside this sub workflow, you can see the weak supervision part that Adrian was explaining. We have the weak label model learner, the weak label model predictor, the gradient boosted trees learner, reading the probabilistic input of the weak label model, and then also predicting, and then this will be retrained at each iteration. Then let's go step by step. If you want to have this workflow, you can find it on app.knime.com. You type in there guided labeling, or you use this marked URL. I apologize that this time is really close to the slide link, and you can download it, customize it all for free on the Knime. So how does this workflow work? We have a first component, the upload component, and this component is actually having this user interface, a button to upload the document, a button to upload the labels, or to manually provide them on the fly. Then we have we have the text processing part first, where the bag of words are created, stop words removal, stemming, all the parts necessary to create the text processing to then train the model. Here we initialize the density score using the graph density initializer node, and then we have another component to provide the rules using this table editor node. Then we start the active learning loop, and we start the human loop. So we need to update the rules, but this is useful in starting from the second iteration in case the user changed the rules. We have the density score, because we want to compute the density of all those rows that are still missing the label. Then we have the initialize and train classifier meta node. This already showed you where the model is trained. And then we have the entropy score, and then we can combine the density and entropy score in the exploitation score combiner. And then finally, we take this score to select with the top case selector what should be labeled next. And then we have here this view that is the one with the tag cloud and so on and so forth that is repeated at each iteration where the user can provide more labels. Okay. Something else. We need to update the density each time new labels are coming out. And then we need to use the active learning loop end in order to repeat the iterations or exit the iteration if the user checked a box in its view. All right, so when we exit the active learning loop, we have this final view with the two-tag cloud and a possibility to download the model or all the labels that we generated. Okay, this was a walkthrough in the workflow that I use for this application. And let's have some key takeaways here. So especially for active learning, but also with the use of weak supervision, we are able now to train a supervised model with less labels than usual. So we can use guided labeling to have a supervised learning model that is using some labeling function, some labels, and this would save us time and money when you use your expensive expert. And then you also have the idea that you can do all of this by building an Knime workflow. You can still code if you want, but by simply adding an Knime workflow, you're developing a web-based application. Another key point is that you don't need a full stack developer to do this. To have usually a web-based application with machine learning training on the back end and interactive views being user-friendly on the front end, you would need a lot of maybe a team of full stack developers to do this. While myself, that I'm a data scientist, I could do it basically on my own. So I think those are good points for this webinar today. Before we wrap up for the sessions, I would like just to point out that at the moment, we are offering lots of online courses. You can find them, and those are about really a number of topics: deep learning, machine learning, data science, text processing, time series analysis, big data platforms, and so on. You can use this code here to have 20% off. And I think this is also great for you to learn more about all those features of Knime, especially if you are excited about using machine learning and text processing. Okay, there is a couple of links here to follow up with us. the Knime blog, the forum, and so on, I would like to express a bit of interest for meetup. We have meetup communities all over the world. Now meetups are not happening anymore as usual because of the pandemic, but we are using those communities to reach out to you when new webinars come up. So feel free to go at this link and register to the meetup group of your area, and also find more Knimers in your area.